1885, Johann Jacob Balmer comes up with this heuristic relationship between the wavelength of a line of hydrogen emission. Hydrogen's a very simple atom, right? It's got one of these and one of these things somewhere out here. And he comes up with this relationship between the wavelength of the line of light that's coming out of the hydrogen spectrum and some constant. He doesn't know anything about what it is, but he's measured the constant right here, Rydberg constant. And this interesting series where n is a number that's 3, 4, 5, or larger. And it makes these lines, and they're patterned in a very beautiful, characteristic way. There's one here, and then there's one here a little bit closer, and the next one gets closer, and the next one gets closer. And maybe they fade into a whole bunch of them all together right here. So that's a cool, that's a really cool observation, but then physicists don't want to get left behind by a school teacher. So this guy Lyman comes along, and he's like, hey, I found another spectrum. It's not in the visible, though. This is entirely in the UV, but he says it looks like this. It's 1 over lambda is Ara times 1 over 1 squared minus 1 over n squared. And the only difference, Lyman says, is that I've got the same r, but my n start differently. It starts at 2, and then I can go 3, and then, well, not 3 again, but 4, and then 5, and then I can go on forever. And then this guy Paschen comes up, and he's like, yeah, I got my own also. He says, well, the problem is, he says that mine is all in the infrared. You don't get to see mine either. But they exist, and you can detect them with instruments, and he says 1 over lambda is Ara times 1 over 3 squared minus 1 over n squared. And Paschen says, no, you don't get to start at n equals 2 or n equals 3. You have to start at n equals 4, but then you can go 5, 6, etc. like that. And then this other guy comes up, and he's named Brackett, and he has another one that starts at 4 here in the denominator, and then that goes 5, 6, 7, 8. And then Fund comes in, and Fund's like, oh yeah, but I've got this other one that starts at 5, and then it goes 6, 7, 8, right? So everybody's getting their own series, and it becomes a bit ridiculous. So the scientific community shut this down and said, we gotta figure out why this pattern is emerging. Something definitely 1, 2, 3, etc. There's really a beautiful pattern here. So let's take stock of where we are. Let's make a list of people who were dreadfully wrong in trying to explain the atom. We'll do it in blue. Who was wrong? The Greeks. They screwed it up, right? They said that atom couldn't be cut. It could. Who else was wrong? Thomson. Thomson was nuts. He said that there was plum pudding or some kind of, I don't know, blueberry muffin or something. Nonsense. A spread out positive charge. That's not sensible. Rutherford, an absolutely brilliant guy in the laboratory, seems to imply that all of matter will disintegrate in a flash of light in less than a microsecond. So all of these have some pretty serious problems. Let's go to a man named Niels Bohr. Niels Bohr had gotten his PhD in 1911. We'll put a question mark after right, because it turns out that he's gonna have to go over here pretty soon too. But for right now, he's doing the best we can. Yay, progress in science. 1911, Bohr gets his PhD. 1913, Bohr shakes up everything with the following theory. Bohr says, remember Rutherford. Rutherford had this nucleus, right? And then he said this electron's going around it, and he said the electron is in an orbit around the nucleus. And the problem with, wow, that's a Bohr twice. All right, this is his PhD. All right, and this is his theory of atomic structure. Rutherford had said, though, that the electron goes around here, but the electron would have to accelerate, and the electron would have to accelerate in towards the center, and as it accelerates, it would let off light, and this would be a big problem. But Bohr says, no, it's cool. Some electrons don't let off light, but they have to be in what he preferred to call his magic orbits. Bohr believed in the presence of magic or stable orbits. I'm gonna put a G there. Yeah, magic orbits. Bohr's magic orbits satisfied just one condition, and that was that their angular momentum, you wanna do capital L? Let's do capital L. My notes are in lowercase l, but we'll see if we can make this work. He said that's ugly. He said angular momentum of the orbit must be, the nth orbit I mean, must be n times h, remember Planck's constant? Yeah, divided by 2 pi. And he says n has to be any whole number. So I'm gonna say n is 1, 2, 3, etc. No, sorry, that's a natural number. N has to be an element of the set of natural numbers. So I guess what Bohr is saying is that God likes some orbits for electrons to have around atoms, and other ones he just doesn't like, so it's not going to be any good. So this is Bohr's statement. Another thing that Bohr likes to say, well, let me get to that page right here. I'm thinking Bohr is saying that yes, an electron moves in a hydrogen atom in a circular orbit around the nucleus. Let's put that in here. Bohr's silly assumptions. Do you kind of get the feeling that this is a little bit silly? I don't know, whatever. 1, electron in orbit around nucleus. Cool. 2, only certain orbits are allowed. Only cool if the angular momentum of the particular orbit you're discussing is the number of the orbit times h divided by 2 pi. These are the preordained and wonderful angular momenta. And his third assumption, stable orbits. Stable orbits, these blessed awesome orbits here, do not decay. Donut? They do not decay in a flash of light. This is handy. All he has to do is say it, and his theory is self-consistent. Because since he can say it, he hasn't decayed into a flash of light, right? Beautiful. And his final statement is that, this is a good one though. He's saying light is only given off. This is brilliant, and I will give it to Bohr on this one. This is a very, very good statement. Light given off only when orbit number changes. That means n goes from 1 to 4, or n goes from 2 to 3, or something. So that's when light is given off. And in fact, he's going to argue that the change in energy of the two orbits, and we'll be able to calculate their energy using, well, we have to use this condition here, and using some standard physical calculations and a little bit of algebra, we'll be able to find the energy of each of these orbits. And he's saying that light is given off in terms of HF, but it's the difference between the energy levels of the orbits. So now he's got a model of an atom that looks like this. There are some protons in here. Now we'll just deal with hydrogen. And there's a stable orbit here. And there's another stable orbit here, and there's another stable orbit here, and these are the stable orbits for hydrogen, and you just can't, what I guess I'm saying is the electron could exist here, or it could exist here, but it cannot exist here, because it's not a stable orbit. The reason it would go in an orbit, I suppose, is the electric force. So let's do a little bit of calculations to try to figure out what falls out of Bohr's 4 assumptions. I hope I don't bore you. It's pretty good, right? Okay, yeah, good. Watch this. I've got a proton in here, and I've got an electron, and I'm going to say this is one of my stable orbits. So the electron, let's say, is going that direction. That's my velocity of the electron. And here's the electron right here. We'll make it seafoam green. I like electrons. Now, the radius is given right here. That's the radius of my orbit. And I guess there's this direction right here. That must be the force on our electron. And I'm going to say that the centripetal force on the electron is the electric force on the electron. So we can find out the centripetal force. That's going to be the mass of an electron, well, times VT. That's the tangential speed. But I'll just write the speed of the electron square. And then I have to divide it by the orbital radius of the electron going around this proton right here. And it's definitely the mass of the electron that is the centripetal force, right? Not the mass of the proton. So I hope you're clear on that. And then I'm going to multiply, well, I'm going to say that's equal to the electric force, which is, well, it's Coulomb's constant times the charge of the electron times the charge of the proton divided by the radius of the orbit square. Now, this, let's go brown. These guys are each the fundamental charge, so I can write that as E squared. And I'm going to solve this equation for m times v squared. So here we go. I get that to be, wait a second, I can cancel out this and that. Cancel out the square right there. And I'm just going to find, this is the mass of the electron, right? I'm going to find it equal to Kc times E squared over R. Is that right? Yeah, I think that's right. And then I want to, well, you remember that we had preordained this, recall, he wants the angular momentum of the nth orbit to be n times Planck's constant divided by 2 pi. 2 pi is really lovely, right? Vi Hart thinks we should call it tau. I mean, wow, I mean tau. No, do you think we should? Do you like pi? I don't even know. All right, so let's take this and then define angular momentum. But the definition of angular momentum is r times linear momentum, which is r times m times v, right? That's the, look it up, it's the definition of angular momentum. So I'm going to say that the angular momentum of the nth orbit is, well, it's going to be r sub n times the mass of the electron times v sub n. This is just saying that if I've got angular momentum and for an nth orbit, it will be meeting those conditions for the nth orbit. So now I'm going to take this statement right here and say this is equal to Bohr's demand, that it's n times h over 2 pi. And we'll just solve this for, what do you want to solve this for? The speed? Let's solve it for the speed of our electron. Let's go for the speed of the electron. Speed of the nth orbit is going to be, let's see, all I'll do is divide by the radius of the orbit and the mass of the electron. So I get n times h divided by 2 pi, put that out front because they don't have dimensions, divided by the mass of the electron and further divided by the radius of the nth orbit. And n can be any natural number. N is an element of the set of natural numbers, which means it goes 1, 2, 3, 4, 5, etc. We're going to come back to this equation right here. So I'll circle it. Turn the page. Next up, I notice something interesting. We're saying that mv squared equals ke squared over r. Remember that? Let's see if I can find that here. mv squared is ke squared over r. We just dropped some subscripts. We can put them back in there again. Mass of the electron and Coulomb's constant. And I'm going to plug in my newly found velocity. Here it is. Sorry for the delay. I'm going to plug in this velocity right here into that equation, and it will be a disgusting mess for a moment because I'm even going to square it. I get the mass of the electron times n squared times h squared divided by 2 squared pi squared mass of the electron squared radius of the nth orbit square equals Kc times the fundamental charge of an electron square divided by the radius of now the nth orbit, right? Because I'm talking about the nth orbit, one of these stable, preordained, awesome orbits. And now I want to do something to this mess right here. I'm kind of thinking we should probably find the radius of the nth orbit. So what I'll probably do is multiply this by Rn square, and then I can cancel that out right there. And then I'll be able to do just a little bit of algebra. Let's be honest, a ton of algebra. Mass of the electron cancels mass of the electron right there. This guy cancels that guy right there. We're going to be dividing by e square, so I got an e square down there, and that guy can cancel out. And then I'm going to divide by kc, and then I get a kc down here. So what I've just concluded is that the radius of the nth orbit stably ordained by Bohr is n square times h square divided by, well, I've got a 2 square and a pi square. And I've also got Kc and the charge of an electron squared divided by the mass of the electron also. And wow, I guess that's it. Let me check my works here and see if I made a mistake. 4 pi squared m k e squared. Wow. 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 This is the orbit. The nth orbit of, in fact, hydrogen. You can plug this in. Plug in numbers for hydrogen. you will find, I really want you to try this. Do you want me to pause it? No, I don't need to pause it. You will find that the radius is, well, let's give an approximate. The radius is approximately 5.3 times 10 to the negative 11th meters, which is about 1/2 of an angstrom, which is the size of hydrogen. This is real. This is real. This actually gives us a perfect result for hydrogen because it's super, super simple system. But remember we had this equation for v sub n, the speed of the nth orbit. The only problem with the speed of our nth orbit is it depended on the radius. And that made me a little bit uncomfortable because when speed depends on radius, it's very easy to get confused. So I'm going to take this equation right here and I'm going to plug back in that the radius of the nth orbit is this stuff that doesn't depend on speed. So I'm going to take this and plug it into that equation right there and see what happens when the smoke clears. Get ready. I've got, well, I don't have to do anything until I get to this, what am I trying to get to? Oh, the r sub n. So I'm going to have n times h over 2 pi times the mass of the electron, and now I need to divide by this stuff right here. So I'm going to multiply by its reciprocal. I get 2 square pi square kc, the fundamental charge, the mass of the electron, and then I have to divide by n square and h square. Ding! Let's clean this up a little bit. Seafoam green can help us with our calculations, our cancellations, I mean. Do we have any h's? Oh, we've got an h down here. That cancels out that one. This 2 cancels that 2 right there. You got a pi? I can cancel that pi right there. You got the mass of the electron. Mass of the electron is gone. Ooh, this is rather elegant. Let's see what this looks like. This says the speed of the nth orbit of an electron in a hydrogen atom will be 2 pi times the Coulomb's constant times the fundamental charge square divided by h. And then I'm going to pull out the dependence on n because it's a little bit of a separate thing. And I multiply it by 1 over n. Let me check my notes and see if I made any mistakes. Yep. Oh, that's awesome. Good job. Now, n has to be a natural number, meaning that it is 1 or 2 or 3 or 4 or 5. So we've got ourselves an equation for the speed of an electron in a hydrogen-like atom. In fact, this works for any electron in H-like atom. And hydrogen-like atoms are atoms that have just a single electron. But they can have any charge you want in the inside. So let's go back to our very first statement that here was our picture of the atom, and we had this charge here, which was plus fundamental charge, and this charge here that was minus fundamental charge. And the total charge then became E squared. So I had to multiply, what if instead of just the fundamental charge in here, what if I add Z times the fundamental charge? Now, Z is the atomic number. And the atomic number tells us how many protons are in that particular element. So we can do this for any element. We will know the radius of the first electron, assuming it's the only electron. In fact, what happens is I go to this equation, and instead of writing E squared, I just write Z times E squared. So I'm going to get a very interesting tweak on each of these equations. I'll go orange with it. Right where I see the E, I'll put a Z times E squared. And I'll put a Z right here also. So I want to talk about this just a little bit. This means that if I've got more positive charge at the center than just one, imagine more positive charge at the center, then my speed will be faster because of the greater atomic number. But, and on the flip side, the radius will be smaller. So if I've got 10 positive charges in here, this electron will be pulled in closer and it will be going faster. All these things are very reasonable. What about n? N is really funky, this index that is making everything happen. I got to put an n in here. N has to be a natural number from 1 to infinity. Let's see if we can make some sense out of what n is doing. But I mean, really, I've just got one more thing to do. I want to take this and I want to write it again in full glory with the z in a nice place. The radius of the nth orbit is h square over 4 pi square kc z e square mass of the electron, and that is it except for a factor of n squared. So if I go to a higher n, my orbit is getting much, much bigger. Very interesting. The orbit is getting much, much bigger, which means one of my earlier pictures is completely nuts. So we're going to stop right here, and then I want to think about energy next. What do you think about energy? Because energy is next. Remember, we're going to have to think about energy transitions. If we're going from one energy level to another energy level, then Bohr is saying that we can emit light. Ultimately, we're trying to explain what Balmer realized heuristically. Good luck. Come back for the next video. A beautiful characteristic way. There's one here, and then there's one here a little bit closer, and the next one gets closer, and the next one gets closer. And maybe they fade into a whole bunch of them all together right here. So that's a really cool observation, but then physicists don't want to get left behind by a school teacher. So this guy Lyman comes along, and he's like, hey, I found another spectrum. It's not in the visible though. This is entirely in the UV, but he says it looks like this. It's 1 over lambda is Ara times 1 over 1 squared minus 1 over n squared. And the only difference, Lyman says, is that I've got the same r, but my n start differently. We'll do it in blue. Who was wrong? The Greeks? They screwed it up, right? They said that atom couldn't be cut. It could. Who else was wrong? Thomson? Thomson was nuts. He said that there was plum pudding or some kind of, I don't know, blueberry muffin or something. Nonsense. A spread out positive charge. That's not sensible. Rutherford, an absolutely brilliant guy in the laboratory, seems to imply that all of matter will disintegrate in a flash of light in less than a microsecond. So all of these have some pretty serious problems. Let's go to a man named 1885, Johann Jacob Balmer comes up with this heuristic relationship between the wavelength of a line of hydrogen emission. Hydrogen's a very simple atom, right? It's got one of these and one of these things somewhere out here. And he comes up with this relationship between the wavelength of the line of light that's coming out of the hydrogen spectrum and some constant. He doesn't know anything about what it is, but he's measured the constant right here, Rydberg constant. And this interesting series where n is a number that's 3, 4, 5, or larger. And it makes these lines, and their pattern in a very starts at 2, and then I can go 3, and then, well, not 3 again, but 4, and then 5, and then I can go on forever. And then this guy Paschen comes up, and he's like, yeah, I got my own also. He says, well, the problem is, he says that mine is all in the infrared. You don't get to see mine either. But they exist, and you can detect them with instruments, and he says 1 over lambda is Ara times 1 over 3 squared minus 1 over n squared. And Paschen says, no, you don't get to start at n equals 2 or n equals 3. You have to start at n equals 4, but then you can go 5, 6, etc. like that. And then this other guy comes up, and he's named Brackett, and he has another one that starts at 4 here in the denominator, and then that goes 5, 6, 7, 8. And then Fund comes in, and Fund's like, oh yeah, but I've got this other one that starts at 5, and then it goes 6, 7, 8, right? So everybody's getting their own series, and it becomes a bit ridiculous. So the scientific community shut this down and said, we gotta figure out why this pattern is emerging. Something definitely 1, 2, 3, etc. There's really a beautiful pattern here. So let's take stock of where we are. Let's make a list of people who were dreadfully wrong in trying to explain the atom.